Anybody familiar with that?
Yeah, so my PhD topic is actually
Yeah.
on shape memory alloys and additive manufacturing using cold spray deposition with nitinol specifically. So this is
Mhm.
pretty interesting.
Yeah.
What you just saw was a short introduction to the invitation I had to give a show at Worcester Polytechnic Institute. Please help me here. We are in US. Do you call it Worcester? Do you call it Worcester? I need some help. So if you know how to pronounce it, please put it in the post comments below this video. I was invited to give a challenge on material science to students at the institute. My old friend Thomas Christiansen is a professor over there, and he invited me to challenge his student. So 41 students was invited, and I had a fantastic day talking to them and introducing them to some material science that they were not aware of, and some of them were pretty smart. So follow this and learn more. Unfortunately, it was made in Zoom, and Zoom and my system are not really friends. So I had some problems with the screen, and I was not allowed to share my screen. So what you see on the screen is not really what I wanted to show. But if you listen, I think you can still learn a lot. So enjoy the show.
So, yeah, welcome everyone, and my pleasure to introduce our speaker today, or perhaps you should say guest instead. I'm not sure how much you're going to speak. So this is Peter Kjeldsteen from Denmark. So I think we've known each other for quite some years. Also,
Yeah, we do.
we've been both been active in the Danish Metallurgical Society. But Peter has a background in steels, which I think is really nice. So he has been working for many years ago on spray forming of steels. And in 2007, you moved to the company Sensex, where you've been involved in research and development. And that's a company working with the powder metallurgical components. And I think the company is still affiliated with Grundfos in some way.
Yes.
So very much into metallurgy, material science, materials technology. So besides doing R&D, you're also very active on YouTube and doing podcasts and kind of disseminating all the good things about material science, which I think is really great. So you volunteered to do a session here with us today.
Yes.
And that's called the Materials Technology Challenge. So it's not kind of a normal presentation. So I think the idea is that you will be challenging all the students and perhaps also me. I don't know. We'll figure out.
Yeah.
It has to be very much interactive. So I really encourage anyone present here to kind of engage in the questions or whatever you have in store for us. And I also want to state up front that I think the plan is that it has to go on one of your channels afterwards, perhaps in an edited format. So if you have any concerns of being part of a kind of a public session, now you know. So you can if you don't want to have your camera on, and then it's also okay. But just so you know up front. So I think I will give the to Peter and get started with the session here.
Thank you very much, Thomas. Yeah, I was called in this Sunday, so I had plenty of time to prepare next to my job. But my idea was to go into different metallurgical subjects, not go deep in one, but look at a lot of different areas, like I do on my podcast, because I typically invite the top experts in Europe to talk about their theme. And that's the way I learned that the world is a lot more than just powder metallurgy. And I would like to share some of this knowledge with you. And hopefully you are also able to teach me some new things today. Then let's jump into the first subject. What is 4D printing? You have all heard about 3D printing, but what's the meaning of 4D?
I think if anyone has some input here, or I think you just perhaps you can also raise your hand.
Yeah, so I'm a little bit familiar with 4D printing. A friend of mine, he works at the Miami University of Ohio and works in that area. But basically, the fourth dimension is time. So she prints things in PLA that then at some time later they will change their shape to become something else.
I have somebody in the background that talks a lot.
Could you just mute if you're not saying anything, because we have a lot of noise. Great.
Wow, thank you. Helped a lot. Yeah, it has something to do with time. That's right. And especially when we look into what is called shape memory alloys. Shape memory alloys typically work when you have time or you have temperature on it, meaning that you can 3D print in a shape memory alloy in a very complex shape, but then when putting it into a hot environment afterwards, it will change geometry or dimensions. So you can print something that after some time will change. Are you familiar with shape memory alloys? And if you are, please help me point out some applications of it.
One into shape memory alloys, there must be.
If I recall correctly, there was I was actually saw this, funny enough, in a materials class recently. They're developing something akin, they're reinventing the wheel for the rovers, for the Artemis missions using shape memory alloys, from what I remember.
Yeah, that's right. The Mars rover has wheels in shape memory alloys. So that's a good example. It's also used in medtech. Any idea why?
I believe it's used for stents as well.
Yes, it is. So you can 3D print today a stent. You can make a scan of your artery, where if you need a stent in your artery, then you can scan it and 3D print one that fits perfectly for your body alone. But then to insert it is pretty difficult because you want to put it through your leg and all the way through the oars to the heart. But when you have it in shape memory alloy, you can squeeze it together in a small, very thin piece and keep it cold. Then when it is in place in your aorta, you remove the cooling of it. And then because it gets the body heat, it grows and it fits perfect in your body. So that's one of the future applications foreseen for 3D printing in shape memory alloys. Then I could give a last one. When you go on an airplane, you want the position of the wing to be perfect, aligned to save energy or to go faster. And if you can adjust your wing position, the tip of the wing, as a function of the temperature, so the faster you go, the more air resistance you get, then the hotter it will be. But then you can change it as a function of speed or a function of temperature, so it fits to the speed or exactly what you want. So that's a smart way of making thermomechanical adjustment of the plane in flight. Then there's this alloy typically used. It's called nitinol. Anybody familiar with that?
Yeah, so my PhD topic is actually on shape memory alloys and additive manufacturing using cold spray deposition with nitinol specifically. So this is pretty interesting.
Yeah. Can you give a description on how it works and what is the composition of it? Because the composition has to be extremely precise to fit exactly the temperature you want.
Yeah, so nitinol is made of pretty much equiatomic nickel and titanium atoms, and they have this really interesting configuration. So at higher temperatures, you're in this austenitic, more of a cubic structure, and then when you're at colder temperatures, you're in a martensitic D-twin state. And the martensitic phase is really, really interesting because it can accommodate a lot of stress. And then when that stress is removed, it can go back to the austenitic state, but it also has temperature dependence as well. So you can deform in that martensitic cooler state, and when you heat it back up again, it'll return to the original shape. And it is really, really sensitive to temperature. So one of the main problems with like additive manufacturing is that you get like heat affected zones, or you have like the nickel content vaporize out. And I think it's something insane like 1 atomic percent difference, or sorry, 0.1 atomic percent difference can change your transition temperatures by almost like 100 C. So it's really a lot of challenges trying to 3D print, because when you heat it up, you can vaporize out some of the nickel that you need, and then you also have problems with any shape training that you've done before. So what we're trying to do is we use cold spray, which is a solid state process. So we take nickel powder and we are depositing on nitinol powder, and deposit it on nitinol substrates and other materials to try to keep those properties retained. So it's a really, really interesting material, and you could spend years and years studying it and still not understand how most of it works.
I perfectly right. I am so amazed of the difference that goes in the temperature just by exchanging a digit of the chemical composition, and I think that was also why it was so difficult to find this property, because it was difficult to reproduce when it was first found. We'll jump to a new subject. Rare earth magnets. Anybody working with rare earth magnets? Anybody who works with rare earth magnets? No. Anybody who knows why they are called rare earth minerals?
It's not because they're necessarily rare materials, but because they have rare properties. That's what I typically understand.
Yeah, it's pretty right, and the story is really strange. The original chemist who found these minerals first, about 200 years back, was a Swedish guy, and when he found them in the ore he was investigating, they behaved very strange. And in Swedish, strange is called the word sällsam. And then when he told other people about it, sällsam was translated to seldom. And seldom is more in the family of rare. So therefore, and the bad thing is that when it was translated back to Scandinavian, Danish, Swedish is same family of languages. Then it was translated back once again, but with the wrong word on it. So it was today in Scandinavia, it's called seldom materials. So it was misunderstood, the wording. So that's why they're called rare. Do you know 3 fundamental magnet types? So if we look around it, we have the neodymium iron boron, but do you know other magnet types that exist out there?
Come on, just raise your hand. I think someone should be able to chip in here.
You are also allowed just to talk. The magnet you have on your fridge, is that a neodymium iron boron magnet?
As a neodymium magnet, right? That should be a permanent magnet, yeah.
Yeah. A neodymium is it's a permanent magnet, yeah.
But you also have electromagnets and geomagnets. Is that what you mean, or do you mean other materials?
Yeah, an electromagnet, it's fine, but I'm also looking for other materials.
I mean, ferromagnets is just old school magnet, right? Metal.
There's the ferrite. So a ferrite is an iron oxide magnet. That was the original magnet found several thousand years ago in Greece. So that was the foundation for a compass. Then when I went to school, the magnets we played with were alnico, aluminium, nickel, cobalt magnets, typically shaped like a horseshoe. But recently, there are also magnet type like samarium cobalt. They are designed for high temperature applications. So today you can make samarium cobalt that can stay magnetic up to around 450 degrees C. And the latest that is it's maybe not on the market today, but it is being developed by an American company named Niron. It's an iron nitride magnet. So it is a magnet type that is without rare earth elements. So it is a magnet that is based on abundant materials. We're not depending on other countries or other regimes. So, do you know what the problem is when we talk about rare earth magnets? Is it the mining or refining, and why? Does anybody know where these minerals they are mined?
I mean, mining occurs all around the world, but I think most of the processing and a lot of the mining occurs in China. And so a lot of the issues with mining and refining of rare earth minerals has been that China has a bottleneck on this. And so if we're going into a period now where if that supply gets choked off, then we're going to be lacking a lot of these critical minerals for magnets and other purposes.
Yeah, that's perfectly right. I think it's around 65% is mined in China. But the mining resources around the world are extremely large. It's distributed all over the world. But refining is more than 95% in China. So even in California, you have the Mount Pass mine. They mine these minerals, but they ship them to China to get them refined. So we are today still pretty dependent on the Chinese processing, and the reason for that is that it's dirty to make the refining, and in many Western countries, when this was developed in the 80s, this dirty process, nobody wanted that. So we shipped the problem to China. So we chose it ourselves. And today it's almost impossible to get back, because refining of these materials is very difficult, and it demands very high skilled metallurgists. And the problem was that at the end of the 80s, we stopped educating people who knew about it. And those who knows about it today, they are either living in China or they are retired. So if anybody of you wants to have a safe job in refining, I could recommend to look into refining of rare materials. We jump to the next.
Yep.
Anybody who can share with us what high entropy alloy means?
It's when you have a lot of components in an alloy. So typically it's mainly like 2 to 3 elements, but maybe I'm not sure what number exactly, but maybe like more than 3 or more than 4 elements are major components.
Yeah. There is something special about it in the crystal, in the phase diagram. It's typically a single phase. So typically you need the core, or the original definition was that you needed at least 5 metals to be in a high entropy alloy. And when blending it, it should not come out as several phases. It's a single phase. So it's a perfect mix. And what makes it special is that these different elements, when they are, if it's a BCC crystal structure, then you have larger atoms and smaller atoms in the same crystal structure, and that gives special properties, because you have tensions in some places, you have place for movement in others, so it can affect your properties and especially the mechanical properties. Do you know about the steel banana?
No.
When Thomas and I we went to school, what do you see the picture at the bottom of the screen?
Yes, the one with the high entropy alloys and materials, the diagram.
Yeah.
Yeah.
On this diagram, you can have high strength on the x-axis, and you can have elongation on the y-axis. And when I went to school, you could not have both. If you went to high strength, you had very low ductility. Or if you went the other way, for high ductility, you had low strength. So this curve down here at the bottom, that's called the steel banana. But the alloys up here, you can see the high manganese or the TWIP alloys. They were developed about 15, 20 years ago. They didn't exist prior to that. But when these came, suddenly new applications also appeared. And you can see this is called a high entropy steel up here, because it's a steel that makes a single phase with a lot of elements in it, different elements. And it could be manganese, it could be aluminium that you add to it. But what kind of properties could be improved using high entropy alloys? Do you have some ideas for it? And now we talk also functional material or functional properties, not only mechanical, because mechanical is maybe the easy guy in the class. But do you think a property like heat conductivity could be improved?
Yeah, I was gonna say in terms of like heat and like electrical conductivity, it's a little bit more going on there.
Yeah. I heard a dream of being able to make a battery where the battery material is also a mechanical material, so you can combine. Because today, if you drive an electrical car, you have a battery of half a ton in your car. But if your battery could be the frame of the car, then you don't need to add all these extra kilos that you just carry around. Then your mechanical structure is the battery. So that is one of the dreams people are looking into. And if we look deeper into these alloys up here, where you have both very high strength and you have very high ductility, could you give an idea of an application for such a steel?
Anyone?
It could be,
You're very
it could be military application.
No one has an idea about this? Any suggestion?
Yeah.
It's a challenge.
If you have a tank and you drive around in it and somebody shoots at you, the armor on your tank, what should be the property of that?
I have an answer.
Yes.
It needs to be high strength ideally, so that hopefully it will deflect whatever comes at you first. But if it does go through, you want it to deform rather than spall and create like things that will kill people on the inside. You would like it to not shatter.
Yeah, you want it to absorb the energy. And the absorption, the energy absorption is the area you have below the curve. So if you say it has elongation on 70% and a strength of 800 megapascal, then the entire area below this curve corresponds to the energy you can absorb. And if you look at the banana, materials on the banana, they are about 4 to 5 times lower in energy absorption level compared to a high entropy steel. So I would build a tank in this material if I had to drive in it.
What kind of material would you choose, Peter?
These high entropy steels are pretty new, but it's iron based, and then they can contain something like 15-20% chromium, 10% aluminium, 15 to 20% manganese. So very, very strange chemical compositions. I'm changing to next theme. So I think I just have to jump out and jump in again.
I have a question before you change.
Yes, please.
How is it with processing these materials?
Very good question. Today they are processed as standard, so liquid. You make the melt and you cast it. You can still make plates out of it at high temperature. But it is it can be difficult, especially you cannot cold deform it because it takes a lot of energy to do that. So it's always hot deformed, and the trip steels that are also very high on that are used in cars, and the next theme I have is in fact on that. So I'm just sharing my screen so you are able to see that. Do you see it now? Crash absorbers.
Yep.
Yeah. If you go in a car today, the chance for survival if you're in an accident is 10 times higher than it was just 30 years ago due to crash absorbers. But do you know other places where crash absorbers are used?
Leave guardrails also.
Yeah, so in train, is that what you mean?
No, on like the sides of roadways.
Okay, yeah. You could call that, yeah. Especially for when they are repairing, then they have a truck in the back, and if you fall asleep and you don't see the people, the road construction going on, then you bump into that truck. But there is a crash absorber on the back of it that makes both the driver and the workers survive. But it's also used in trains, and it's used in elevators. So if you're on an elevator and it starts to fall, then you have both magnets trying to catch it or to slow it down, and you have at the bottom crash absorbers that absorb the energy. So you might break your legs, but you still survive. So now you should know this question, or you should know the answer to this question. Which material properties are important for crash absorbers?
Impact energy.
Mm-hmm.
The failure should be ideally ductile failure. It should not, the flanges should not open apart,
Mm-hmm.
so that it exposes the people sitting inside.
Yeah. And then when you typically, if you have an accident like this, it's a very high speed, and typically when you make test of mechanical properties, I guess you have done that in the lab, making tensile test bars and trying to pull them. Have you tried to pull at different speeds?
Yeah. So the test we did at here at WPI is lap shear, the peel test, and the impact energy test to basically break open this coupon joint using some adhesives and sealants, because today the welded joints have reduced a lot. The major joints in automobile are adhesive and sealant based, because this adhesives and sealant based joint decrease the weight of car and increase the fuel economy, and at the same time giving same kind of crash resistant and the joining properties.
Mm-hmm.
So we tried different rates, but all those rates are standard what GM or Ford will float out in their standardization sheet. So for me, it was something like, I think 10 millimeter. It was it was a high speed. It was a very high speed
Okay.
breakage. Yeah.
Yeah. Carlos, my friend who is on this photo, has been developing crash absorbers, and he worked at a company in UK where they had a test facility. They had a tower that was around 15 meter tall. So that's what is that, 45 feet. And in that tower, they could lift up 12 tons of material and then release it. And at the bottom, they placed crash absorbers to test how they worked after being hit by 12 tons coming down with a speed of, I think it was around 60 miles per hour. So that was the most crazy test I have ever seen. And here I have a curve, or some curves, showing that the properties, they vary depending on what speed you are running at. So for all materials, if it's plastic, it's very depending on the speed. If it's steel, it's a little less, but all materials, they have a dependency on the speed. So therefore, the speed you put in your tensile test machine is important to have in your report, because then people can reproduce, or maybe not if you have forgotten it. Yeah, we jump to the next, biomining. Anybody familiar with biomining?
I know bio leaching. I did some for, I don't know if it's the same thing, but
Yes,
I
it is.
did some bio leaching for extracting some manganese and lithium from the spent batteries. Like, yeah.
Yeah, it is very similar. Leaching is one method within the world of biomining. Can you tell what goes on in bioleaching?
So we have a culture of bacteria. So there are like different class of bacteria, and so it's a fungus, so it's bacteria. So we grow this bacteria in an environment, and then expose the spent batteries. So we cut open the batteries, we spread it out, and we basically dump these batteries into like the raw material of these batteries into the tub with the bacteria in the bacteria colony, where we let it grow under some humid environment, varying different parameters like temperature, the volume ratios, I mean the water and the solution ratios, different acid conditions like oxalic acid or basically varying that acid concentration.
Yeah.
And at different time steps, we see how much of the it has converted into oxides or different hydroxides, and basically from there take it down and convert it into purer form of the metal.
Wow, perfect. Thank you. I love your explanation. The original standard leaching is on copper, because copper is typically found in nature in copper sulfate, and the first bacteria on the earth, what should they live off? Because when they started to grow some billion years ago, there were no organic material. So they were living off heat from the sun and the sulfate or the sulfur from different sulfates. And copper is typically found in as a copper sulfate in nature. So these bacteria, they are the very old kind of bacteria, the first generation of life on Earth, and many of them are not able to survive in air, because when they were invented, when Mother Nature started these bacteria, the atmosphere was zero oxygen. So for us, the atmosphere would be very toxic, but for them, it was fantastic. So if they come to surface, if they are out in air, they die. So they're not dangerous to us. They will die if they meet us. So therefore, they are often grown in tanks without air and high acidity level. So as you described, add acid to it and they love it. Do you know if it's a new thing or if it has been here for long to use biomining?
Not sure about that. When I was doing literature survey, I could find something like the till 2008, 2005, I was able to find material on that. One thing unique I found was that the yield is very dependent on the feedstock size. So the particle size is very important because the bacteria can only act
on the surface,
or do the reaction till one particle size.
Exactly, yeah. In fact, the way the Romans 2,000 years ago harvested copper was using biomining. They didn't know that it was bacteria because nobody knew about bacteria at that time. But that was how they refined the copper out of the ore. So it has been used for many, many years. Do you know if it in industrial today?
It's definitely not industrial. I mean, I have not seen any industrial like wide scale industrial application. There is some work, but it is all like pilot scale work. There are technologies which use nature in some way to extract, but it's not the bio or bacteria based treatments.
Yeah, in fact, it is very well spread, especially in copper industry. over the last 30 years, many abandoned mines in South America, they have been reopened using biomining. The yield of the mine when harvesting traditionally was too low, so therefore they were abandoned 50 years ago. But today they have reopened, and today about 15% of all the copper mined today is mined using biomining. Gold as well. It's also a pretty large percentage of gold harvested today is biomined. So it's really a process that is growing. And one of the advantages is that in nature, copper is often seen together with arsine. And arsine is a very poisonous material. It can kill everything. And when you make the metallurgical melting process on the traditional way, you put it in an oven and you roast it. And when you roast it, the arsenic evaporates, and then it condensates in the area around the melting facility. And that means if you have a roasting area in the fume wind direction, you typically have an area that is 2 to 3 miles long and about 1 mile wide, where nothing can grow because arsenic is condensated in that area. But when using biomining, these bacteria, they don't want the arsenic. So you can perfectly separate the copper out of the ore, and only the copper, by using this, and then leaving the arsenic in the residuals. So it's environmentally a pretty smart way of mining. Then I made an episode on the podcast with Lynn Rothschild from NASA on using biomining in space. Have any of you heard of that as a possibility?
No, but I guess it makes sense based on your discussion. I guess if you use it on Mars, you could potentially extract various resources in situ for if you're going to set the stage for production locally, I suppose.
Yeah. They have, in fact, taken it one step further. They have they're using fungi, and they have what is that? Gene modified fungi inspired by hemoglobin, because in your body hemoglobin can attach to one metal, which is that? Anybody know what hemoglobin loves to
iron, I believe.
Yeah. Iron, yeah. Can hemoglobin attach to nickel or cobalt or chromium or copper?
If modified, maybe.
No, it cannot. It is defined, the protein in the hemoglobin is designed only to take iron. And at NASA, they have found other proteins that are designed for specific metals. So they have one for nickel, they have another for copper, they have another for gold. So therefore, they have this living material. You can bring it in a suitcase, 17 different materials, and if you need gold and you're on Mars, you cannot call back and say, please send some gold next time you ship a carrier. Then you go in your lab, you grow your product, you take your ore, and the mycelia, the product from the fungus. The mycelia is designed to only separate the gold out of it. That's a pretty smart way of making separation.
So you would use hemoglobin to bind the resulting iron from leaching from the ore, and then transport it with that. Couldn't you then use the hemocyanin from horseshoe crabs to bind copper instead, for instance?
The protein copied from hemoglobin takes the iron, but another protein that can catch the copper is then gene modified to attach to the mycelia. Okay. So you have different species of the mycelia that you bring with you. Does it make sense?
Yeah.
Yeah. Has anybody of you got a bone implant? Have you broken your leg and got an implant, a metallic implant?
I have about an 8-inch long plate in my right leg.
Mm-hmm. Yeah.
From breaking my leg in February of 23.
Yeah, and how many surgeries did you have? Only one, or did you have another one?
I've had a total of 3 surgeries, though the third one was just to remove scar tissue in my knee.
Yeah. So the idea of using magnesium is sorry about these bad-looking photos. But you see, typically when you break your leg, you put in a metallic plate and screws to help it grow. But these implants, they are strangers to the body, and very often the body starts to attack it. Can you mute, please? Oh, thank you. So if you, instead of using steel, if you use a magnesium, then it dissolves. So your body doesn't need it. It's only there to secure that your bone grows. But when your bone is grown back, then you still have your stainless steel or your titanium inside. But if you use magnesium, it will dissolve. And when it is dissolved, or when it dissolves, it leaves space for the bone to grow. And one of the advantages is that your bone, what is it made of?
Calcium and calcium.
Yeah, calcium and magnesium.
Oh.
Yeah, it's made of calcium and magnesium. So you give the bone something to grow off. So it is really fantastic. When you put in magnesium, your bone growth will be increased. So you will cure yourself faster than you do normally. But then the chemical reactions happening when the magnesium is dissolved, could you imagine a gas being formed inside your body? Have you tried to put magnesium in water?
It would explode.
Yeah, and why? What gas is formed?
Hydrogen?
A hydrogen, yeah, that's perfect, right. So hydrogen is actually produced when the bone grows back and the magnesium is dissolved. But the good thing is that our body, our skin, is permeable to hydrogen. So if you just can ensure that the degradation of the magnesium is slow enough to not produce too much hydrogen within a short time, but dissolve slowly, then the hydrogen can diffuse out of your body without damaging you. And then they also add rare earth elements like gadolinium. And the reason for that is that if you have pure magnesium, it simply dissolves too fast. So they're developing the alloy system to fit with the speed of your bone growth. So it means that if your bone can grow with 1 inch per month, then the dissolving of the implant should be corresponding to that with 1 inch per month. So by adding gadolinium, they make it fit perfect to you, and in some patients they adjust the chemical composition. If you are a fast grower, so small kids, they grow faster than old men. So for small kids and for old men, you need 2 different alloys to fit it with the bone growth speed. So anybody ready to jump into medtech industry and design next generation materials?
Potentially, maybe, yeah.
There's absolutely money in it. I can tell you. So, Thomas, I came to the end.
Yeah, I think it's 1 o'clock here. So thank you very much for enlightening us with very different topics. So I learned something on biomining that was actually quite new to me. So
thank you very much for following. I hope you enjoyed it and you learned a lot, because in this episode we went through several different technologies that has been on episodes on this podcast before. If you want to learn more, or if you want to check if my memory was right, I will encourage you to take a deeper look into the previous episodes. If I was wrong, I would be happy to be corrected. So please help me and help yourself to grow your knowledge in material science. See you in the next episode. And next episode, that will be on thermal measurement, where you are able to measure on a spot the size while it moves in a 3D printer. Because my next guest has developed a technology with a laser measurement to be able to adjust the temperature on the deposition extremely accurately to produce exactly the same every time. That is just what the 3D printing guys have been looking for years. So tune in for the next episode and learn more. See you.